Yes.
Oh wait, I have turn on camera. Okay, guys. Unfortunately, you aren't getting the bunny ears this time. Uh, I know. I too am disappointed. Okay, wait, let's see. Let's see what we have to do today. Oh God, that's too big. Mm, so guys, technical difficulties here. Ignore. Why are you disappointed? I shall not speak in truth. Guys, please, please. If you behave this time, there will be many years next time. Trust me. Or in fact, if you behave like later in this class, there might be no promises. Anyway, okay. So you all know Euclid's GCD algorithm, but I'll just recap. So okay, first of all, given any integer a, given any integers a and b, where uh, b is not zero, there exists q and r in z with nothing. The class has just started, Anirudh. Uh, Unique. How do I write unique? There exists. This might have been a unique. Okay, such that a equal bq plus. Okay, so everyone knows this, right? NP. So I'm gonna cover things like just the division algorithm, the GCD algorithm, Bezout's lemma, and maybe some infinite descent. If we have time, we are jumping, but that's slightly beyond the scope. Anyway, okay, so everyone knows this. That given any two numbers, there's like a unique quotient and remainder. This is all that's saying. Okay, so what you do is suppose you have one thing, uh, a comma b. Okay, when I write a comma b like this, I mean the GCD of a and b. Okay, the, first here's this claim: a comma b is a comma r. Why is this? What do you mean by unique? There's only like one Q and R, like only one pair Q and R satisfies this, where R is in this range. Because it's Akshit, is that clear? Like when you divide, there is one quotient. Like it can't be like 3 okay, not 3 is too small. 15 can't be 2 into 7 plus 1 and also be 2 into 6 plus 3 or whatever. No, that doesn't work, but like you get the point. It can't also be 3 into 7 plus 2. Uh, what? Yeah, that's the point. There's only one. Hmm. The reason it's unique is because we have fixed the remainder to be in this range. Yeah. First, does everyone can anyone prove this quickly? That the GCD of A and B is the same as GCD of A and R.
Yes. We can say that A and B have the same set of common divisors as A and R.
Yeah. Anything that divides A and B must divide R, and anything that divides A and R must divide like either B or Q. Yeah. Yeah. It must divide anything that's A and R. Wait. One last question here. Yeah, anything that divides A and B must divide A and R. So their GCD also divides the GCD of A and R. That's one direction. Can you prove the other direction?
What are we trying to prove?
We are trying to prove the GCD of A and B is the same as the GCD of A and R.
All right.
I think this is true only when the GCD of Q and R is 1.
I'm thinking, wait, what's some skill issue going on here? No, this is always.
If we plug in BQ plus R into A in both the things, then I
Oh,
guess
sorry. Yeah. I replaced the wrong thing. It's supposed to be equal to R and B. My bad. My bad.
Yes.
My bad. I was also like, this does not seem true. Yeah.
Okay.
Yeah,
So
and now everyone can see anything that divides A and B divides R, anything that divides R and B divides A. Skill issue happens. It's fine, guys. I was like, this does not seem true. How? That's why I was like, can anyone prove this? Because I was not sure why this is true. So, I love complex bash. Very interesting person here. I approve of that name. Okay. Yeah, this is clearly true. So what you do, when suppose you want to calculate the GCD of two numbers, say A and B. So suppose like A is the larger number. When you divide A by B and you take the remainder, now I'm saying A is greater than or equal to B, and we know the remainder is smaller, well, at least absolute value wise, right? So we get R and B. Now remainder is smaller than B. Now you divide B by R, and you get a new remainder, and this is like even smaller, and you keep going, and you will keep getting smaller and smaller numbers. And the amazing thing about the natural numbers is that there is no decreasing sequence, infinitely decreasing sequence of them. You must eventually like stop somewhere at zero. I should have said positive, non-negative integers, not naturals, but it's fine. So eventually one of these becomes zero. So say you get 0 and x, and the GCD of 0 and x is just x.
yeah.
Excellent. Yeah. So this is how you compute like this is the Euclid's algorithm for GCD. You start with two numbers, you keep taking remainders until one of them becomes 0 and the other number is the GCD. And this is absurdly efficient. Like this can like I don't remember the exact. It's like logarithm very fast. I'm not a computer science guy. Don't ask me how fast, but it is pretty fast. Okay. No, this is this is a clear. That's all.
Can we prove this?
What? Prove what? We just
That eventually we'll reach. Okay, you didn't say one, right? Okay, sorry.
yeah, it's a 0. It might not reach one. In fact, it won't reach one. It will reach one only if these two are co-prime because it will reach their GCD.
So can we prove it? It will reach when it's co-prime, when the
Yeah, because something will reach 0 eventually, right? The other
yeah.
number we have shown must be their GCD. That's what we have shown. Right? Because GCD of A and B is same as GCD of R and B. It's same as GCD of R and R dash, and so on. It's same as GCD of 0 and x. And GCD of 0 and x is just x. Right.
But
Uh,
X should. What if X is a divisor of the GCD of R and B and not?
and not.
Sorry. What if it's a multiple of GCD of R and B and not the GCD itself?
No, no, it is always a GCD. That's these two are equal. Like, look here. If any number divides both A and B, it divides R. And if any number divides both B and R, then it divides A. So it's true in both directions. Like GCD of A and B divides R, and GCD of R and B divides A. So they must be the same number.
Okay.
Is that clear?
Uh, I don't understand how do we get the GCD of that at the last in the Euclidean?
Do you get this? Do you understand why the
Yeah,
GCD of A and
I
B and
get it.
R and B are equal?
Yes, I do.
So the thing is, they're equal at all steps. The say one is the GCD of A and B, which is same as the GCD of R and B, which is same as the GCD of R and R dash, which is same as the GCD of the next thing and the next thing, and eventually is the same as the GCD of 0 and x.
Okay, yeah, now I get it. Thank you.
Yep. And hence x must be. Anyway, speaking of which, now we come to a seemingly different question, which is very related. Suppose you have two numbers, A and B, well, actually, again, A and B, which are integers, non-zero. I don't like 0. Consider, and suppose x and y are any integers. Ax plus by slash. Consider this set. The set of all possible ax plus by for integers x and y. So suppose you have like, example, 9 and 6. You have all numbers of the form 6x plus 9y. Right. My question is, what is this set? Can you describe this set? For example, let's start with 9 and 6 itself. For 9 and 6, what can you say about this set?
All the multiples of 3 are.
All the
All the
multiples of GCD or A comma B is the set.
multiple of GCD. Yes, exactly. That is what we'll prove here. The claim is that this set is precisely the set of k times.
Hmm. A comma B.
Oh, sorry. Yeah. K times I could be such that. Hmm.
K belongs.
Yeah. Yeah. Mm. So, okay. First of all, one direction is clear. If any number in this set is divisible by the GCD of A and B. What have we covered? We have just covered Euclid's algorithm for GCD. Someone in chat can explain. Anyway, yeah. Like everyone, like it's clear, like the GCD of A and B divides A and B, so it must divide AX plus BY. So every number in this set must belong to this set. Now we have to prove the other direction, that every number in this set belongs to that set, right? So in particular, notice this. Suppose if we prove that there are X and Y, such like there are X naught and Y naught, such that AX naught plus BY naught is the GCD of A and B, then take KX naught and KY naught. This will give you K times GCD AB, right? So if we manage to prove that we can get we can prove, if we can prove that we can get GCD A comma B, then we can get all its multiples, right? Yeah,
Yeah.
yeah. If anyone has, yeah. So, there's a lot of Sophie kids here today. So there are two proofs. So the first proof is what we did above. Let's this Euclid's algorithm. This is how they're related. So suppose you have two numbers. Let's pick. Give me two numbers. Okay, let's pick 42 and uh, 14. Okay. No, this divides it. 16. So 42. You do the Euclid's algorithm. 42 is 16 into 2 plus 10. Right. So GCD 42 comma 16 equal 10 comma 16. Now you do again. 16 is 10 times 1 plus 6. So this equal to 6 comma 10. Just ensure I'm not skillishing. I'm replacing 16 by 6. Yeah. Now you do for 6 and 10. 10 is 6 into 1 plus 4. So this is equal to 6 comma 4. 6 is 4 into 1 plus 2. So this is 2 comma 4. And finally, 4 equal 2 times 2 plus 0. So equal 2 comma 0 equal to. So this is the Euclid's algorithm for calculating the GCD. Right. Now, from this, you can actually prove Bezout's theorem. I'll give you try to use these steps that we have written, these 5 equations, to find x naught and y naught for 42 and 16. Any ideas? Yeah, okay, Gupta, go ahead.
So basically, like, if we could get x naught and y naught such that x naught plus by naught is AB, so
Hmm.
we would be done. Like,
Yeah.
So we can like apply Euclidean algorithm, and like
Yeah.
in the final step we would get A comma B as some linear combination of A and B.
Wait. Okay. You need to elaborate a bit, but yeah, you have the idea. Okay. So the point is um we substitute back. Like we substitute forward actually. Like mm, look at this step. This step tells you that 2 is 6 minus 4, like 6 minus 4 into 1. And the previous step tells you how to write 4. 4 is 10 minus 6 into 1. So you substitute the value of 4 from this. And then you get 2 written in as a combination of 6 and 10. And then the previous step tells you how to write 6. 6 is 16 minus 10 into 1. So you substitute this, and now you get 2 as a combination of 16 and 10. And then you keep substituting from the previous equation until you will eventually get things as a combination of 16 and 42. Is that clear? Oh, yeah. Okay, if anyone has any doubts, just as always, feel free to stop. But that is okay. There's one more piece of theory we'll cover later on, but that's basically all the theory I wanted to do. So let's do some problems. Okay, so to start with, here's here's a very famous problem. Yeah, immediately everyone figures out what this problem is. I okay. Is there anyone here who has not seen this problem? If everyone has seen it, then I'll just skip ahead. Okay, yeah, it's appears everything. At least the chat has seen it. People who are not chatting, I was six, nothing. No. Do I do this just for okay? I think everyone has seen it. Okay, I'll just do it quickly. I'll write down the proof. So the point is, we want everyone has seen it. Okay, I'll just write down the proof. Yes. Everyone. Plus 3 minus. Uh, the numerator and the denominator, there's a linear combination of them that is 1. And we know that every linear combination of them has to be resolved by their GCD. So their GCD has to be 1. Hence, it's irreducible. I mean, you have to show this question. It's a law. I'm legally bound to show this problem after covering Euclid's algorithm or
Can't you like
something.
directly use Euclidean algorithm?
You can. Actually, don't even have to use Bezout Like, you can just
Yeah,
do repeated division and show their GCD is 1. But, this looks shorter and cleaner, even though it's literally the same thing.
yeah, it's like two lines.
Yeah, this is the very first IMO problem ever, for those of you who didn't know. We have come quite a bit far since then. Let's let's move fast. Let's get to some actual problems.
But this year's IMO problem one has nothing on this.
Yeah. This is the actual IMO problem one, guys. Like now, I don't know what they're asking random stuff. Like back when questions used to like be real. Before NT died, guys. This is the last time NT was alive. So okay. So here's a slightly more non-trivial question. And wait, I'll actually post a few problems because I think some people have also seen this probably. Yeah. Both trivial. Yeah. Okay. Hey, okay, fine. I'll put a problem that is not in Mont. I I do not just steal from Mont, guys. I steal from other sources. Real by theorem. Real by Okay, guys, don't look at this number and figure out the source, okay? Like this can be algebra one for all you know for short list. It's not like it's an NT problem,
But
guys. Come on.
algebra one is still easy.
Shush. I mean, this problem is also not that hard. People who are okay, everyone seems to. Do third problem. Third problem. Wait, have you also done the third problem? Wait, I'll get.
Yes, yes. In
Bro,
fact, I believe it was the first Putnam problem I'd ever solved.
okay, I mean, you might. I think you might have done all the problems for this class. I'll. 'Cause, yeah, I mean, I don't know why you're here. This is. But I'll just. I mean, you've probably also done this. Okay, okay, okay. So number one, Rayansh, I think you have done every problem in this class. You can. I mean, you can stay in chat. Don't spoil the answers for people who haven't. I want to know, has everyone done every single problem I have put here? If that's the case, then this class might be slightly skilled. Okay, forgotten. Forgotten is good. Resolve. There are people who are not chatting, so I think they have not done it. So I will actually discuss these problems. I'll give you guys some time. I think I think a few like people have done it and they're just okay. Isn't P4 is all 29? I mean, prove it. Forgot P2, didn't do P3, done and remember P1 and P4. Okay, nice. So everyone had, I think except Rayansh and Baby Lavish, everyone has some problems to try.
I haven't done P4.
You haven't done P4? Yeah, okay. You try P. I have done P1, P2, P3, and P4. I forgot it. You forgot. Amazing. Wait, let me put one more problem. Well, okay, I'll go through all these problems on my one, guys. Like people who haven't done it, don't worry. I'm just post for people who have seen some problems before. You can feel free to go ahead and try some of these problems. Nice. This is in mode. Damn, guys, you figured out that you figured out all my sources. It's hmm. I wonder which problem this is. Anyway,
Why?
let's. I mean, we have to. Someone has to cover Vieta jumping in
That
OMC.
is the most there is a solution for that with just GCD and stuff.
I mean, no. This the point of this class is to cover all descent-like ideas, and Vieta
Yeah.
jumping is like one of them, right? So which is why like this even this is here, and last three problems are like not related to just GCD and stuff. They're just covering descent-like ideas. Look, someone had to do it. Like someone would have to eventually take a Vieta class and they would have to do this problem. So we have to do it right. Let's just do it right now. Wait, you did? Did you already do this problem? I got two others. Oh, wait. Hey, Devayu, are you saying this was your Inmo? Oh, you did Vieta. Wait, what? Wait, has there been a Vieta class for this cohort? I don't think so. Like last year, I believe. I, I mean, every class has happened last year. But everything is done. Okay. Okay. Guys, ignore all the people yapping, by the way. Like, Ridyansh and Lavish are like, and Debayu, they're all like veterans. Ignore them. New people, please try this problem. Okay. Someone who hasn't, I don't even yeah, but I'm still getting you ignored. Very sad. Can I make a problem? Yeah, I mean, okay, Gupta, wait, am I supposed to recognize you? This is very sad. Guys. Oh my God, that's so. Okay, guys, also ignore K Gupta, like completely. He's just here to farm votes. Let's. Yes, I'll just. Okay, I'll move on to the actual people here. Okay. Also, if anyone has any problems they would like to do, because if anyone has seen these, you can DM them to me. But anyway, new people. Ayush, Vansh, I love Complex Bash, Adyant, Ashatak, Keshav, Nikhil, Anirudh. Okay. Okay, people who have not done these before, let's start with P1.
Can I solve P1?
Have you done this before? Have you?
I did do it, but
Okay, wait. I'll just give some time for people who are seeing the problem for the first time. It's also Debayur. Did you give this info for P5? Yes. Damn. Nostalgia. First info. I got two. It's okay. Today we get 17. That's okay. Wait. I also asked people who have not been talking. Can someone like tell me? Wait. Oh, okay. Half his class is veterans. Like Sanjana has also joined. How many actual students are here? And how many you can always remain a student of the game? True, but I think people who have been here for long do not have seen all these problems before. Or like anyway. Okay, I would what's the time right now? It's 08. Okay, I'll wait till 010. Hopefully can a new person tell the solution for P1? But otherwise I'll just ask Keshav. Keshav, wait, are you done with all the problems?
I have done most of them. I'm just doing the fourth one.
Which fourth one? Okay, you do the fourth one. Are the latest in they're not latest in they are from diverse sources, but Mont also took them. Like, okay, P1, P2, and P4 are all in Mont, and P5 is in Mo. Okay, P6 is also in Mont, but P6 is everywhere. P6 is just like the most famous IMO problem ever. P3 is the one I would have expected
Now
less people
this
to say.
year P3 will become more famous than P6.
I don't think so. 1959 only, yes, yeah. This was the actual problem. This was the best problem of this class. I don't think so. No, surely number five has ensured P6 is the most famous one. Anyway, okay, Keshav, go ahead. What's your solution? What's the solution for P1?
Okay, so without loss of generality, assume that n is greater than m.
N is greater than M. Okay.
Then you, using Euclidean algorithm, you subtract
Okay, well,
a raised to
theoretically
m
they can
minus
be
1.
equal, just letting you know,
Okay,
but
okay, come
that
on.
doesn't change anything. That doesn't change its
Yeah.
sign. I won't-
So essentially what happens is the exponents follow Euclidean algorithm and then you eventually reach the GCD.
Yeah, perfect. So GCDA minus 1 equal GCD Terence. Did Terence still get 1 on 0 on this? I don't remember. So this was, and oh, why am I writing GCD every time? So, And quickly write a proof. One and a to the m is co-prime with a to the m minus 1, so you can get rid of it. And as you keep doing this, the exponents will follow, as you said, Euclid's algorithm. Others, okay, fine. You can do others. I don't like that. There's simple solutions. Don't use nukes. Okay, others. Okay. Does everyone understand P1? P1 is actually like an important lemma, and you should know this. Oh, also, let me just. Someone asked this earlier, forgot to reply. Yeah, you can just cite Euclid's algorithm in RMO without proof. Do not worry. Can you explain what the subtracting do? Okay. Um, Nikhil, like, okay, what I did here earlier is just like true in general, like AB equal AB. In general, if you have A comma the GCD of A and B, then that's the same as the GCD of A times K times B comma B. These two have the same GCD. The point is if any number divides A and B, it also divides A minus KB. And if any number divides A minus KB and B, well, then you can write A as A minus KB plus KB. Hence, the GCD is same. Okay, is that clear? Yeah. So that's what he has done here. You just take a to the n minus 1, a to the m minus 1. You subtract from a to the n minus 1, a to the m minus 1. Then you take some stuff common, and then you get this. So you from nm, you get to n minus m comma m. And you keep doing this until, so exponents will basically follow Euclid's algorithm. And you will eventually get to the GCD. Okay. P2, people who have not seen it. Let's get some new people. I finished before. Very nice. Wait, so you're done with all problems. Wait, let's try to get some new problems. Okay. I think there are still some people trying P2, right? Just letting I'll find some new problems for people who are done with everything. Just can everyone who has seen P2 raise their hand? Just let if it's everyone, then this class is cooked.
Can you repeat what you said?
Everyone who has seen P2 before. Seen but forgot. Forgotten is good. I mean, it's not good for you, but it's good for this class. I can't raise my hand. That's a skill issue. How do I hold up my hand? I don't use Zoom. Yeah. Oh, actually, I don't understand. Okay. You have actually done this problem long ago, but I have forgotten how to do it. So we'll people who have already seen everything in the class can try this problem. I have done. Oh my God, guys, it's this class might not be for you then. Not gonna be. Wait, was this on Sophie P set? Okay, like everyone here isn't in Sophie. That's fine. Sophie students, this class is slightly above your level. Below. Okay, you can lower your hands. I think everyone didn't raise their hand, so we can hope. So please. Okay, where are the new students? Why are they not talking, by the way? Like, I don't use all this. I'm not the notice. It's like chat is just memeing completely. But IMO 2024 P2. Okay, we can do that. Okay. I think there are plenty of people in the class who haven't seen these, by the way. I will just do them for them. You guys can try whatever problem Ridansh recommended. Sophie schools. Anyway, okay, new students. Any ideas for P2? People who haven't seen it before. Okay, Vansh, yes, go ahead.
Yeah, so we can write it as GCD of mn times n minus 1 choose m minus 1 and we are done.
GCD of MN as?
N minus 1 choose m minus 1 by subtraction because n is greater than equal to
Hmm.
m, and we see that if n is equal to m it's trivial, so n must be, we can see the case n strictly greater than m, and we can just subtract n, like cancel n from n factorial, and we can still cancel m from n factorial because m is obviously lesser than n, and we get n minus 1 choose m minus 1 times the GCD.
Wait, no, I'm not. I don't follow. What do you do? You write N choose M as?
Okay, so just open it and it would be like n factorial by m factorial by n minus n factorial, right?
You just write it as this.
Yeah, and we can subtract the n on the denominator in the complete expression, right? It would be n minus
Yeah,
n factorial, and we can
yeah,
see that n is equal to m case is trivial, so we let that
yeah.
m is greater than m. So we
N is
can
greater than
still
M.
subtract m from n minus 1 factorial, the cancel out, yeah, right?
Okay.
So it would be something on the above
Yeah, but
and
that
oh
doesn't
yeah.
prove. Then you will not be left with just a factorial here. You can't write it as like N minus 1 choose N plus 1 because then something from here disappears if you cancel the M.
So we can write the GCD of Mn as mx plus ny.
Yes.
Yeah, we can do that then.
Right. And then what? Wait, let's go down here actually. I mean, you can try N4 or N7. I don't think they're appropriate for this class. Like, it's fine. Yeah. Okay. So you write it and you use Bezout's lemma. So you write GCD of NM as NX plus MY. Now what? What?
Can you show me the InMo problem? I want to take the screenshots.
Yeah. Yeah. Can also just search it.
Yes.
Divide by n and expand. Yeah. Yeah, okay. So I think people have figured it out. Yeah, yeah, exactly. Okay, so, equal. Yes. Okay, does everyone understand this proof?
Yes.
Okay, maybe more. Is there anyone who doesn't understand this proof? Hmm. Okay, I think everyone does. That's nice. So in general, whenever you see like GCD, it's like, okay, sometimes you can handle it normally, but in this problem, doing anything of this sort, like keeping it as GCD is very hard. So just try to write it as nx plus ny. Okay, now P3 is a new trick. I'll wait for everyone to try it for a bit, but this is
Can P2 solve using another method?
P2.
Yeah.
Uh, I'm not sure of a different solution. There might be. I'm not aware of one. Do you have a different solution?
No, I don't.
Yeah. No. Okay. Okay, for P3. Okay, everyone try P3 for a bit. Yes, once you are correct. That's technically true. How will this can be done without Fermat's descent or VP? Without P3, I mean, many such problems have multiple solutions. I'll be doing the Fermat's one, but I'm interesting. There's a different problem. Wait, is this also in Mont? Okay, I know the solution using descent. This was Putnam 2000 B2, the P2. Let's solve Putnam. The entirety, like, not here, like, maybe. Let's do IMO 2025 P3. No, please stop giving me drama. I think the early Putnams are usually break. The last ones are very hard. B1 Like, if we have like a 3-hour class or something, no, that will still be not enough. Like, okay, I don't even know enough group theory and linear algebra to do some of the problems. You know what? If you keep annoying me, I'll take a Sophie class and we'll just sit and do Putna P6s. Okay, that excited them, that didn't scare them. Hmm. This class is missing. Anyway, new students. Once again, ignore these guys. Yeah, you please try this P3. Okay, P3. Okay, what do you think the answer is? Can you keep doing? Yes, yes.
It's infinite.
Nishkarsh, can you? Your idea is correct. Can you just elaborate on it? Can you unmute? No, you're not unmuting.
Okay, so yeah, can you hear
Okay.
me?
Yeah, I can hear you.
Yeah, so the idea is that we can just keep like, for example, right now we can do that b divides 2 and then
Two
when
divides
we
B. Two
expand
divides
then
B.
we can cancel b out.
Two divides
Yeah,
B. B
sorry, 2
doesn't.
divides b.
Hmm. Okay.
Yeah, and then after that, when we do that, we can cancel b out and then we can do 2 divides a. And then this just keeps going on in an infinite descent. And that's why
Okay.
there's
Wait.
no
We
solution.
Yes, that is okay. That's fine. You are correct, but okay. That's not exactly true. Okay. For n equal 1, we have the equation 2a plus 3b plus 4c equal 4c. And this one does have a solution. Uh, for example, take 2 comma 4 comma 4. Oh, or take 1 comma 2 comma 2, I guess. This is a solution of this equation. Right. For n greater than equal to 3, what he said. Okay, so we have 2a to the n plus 3b to the n equal 4c to the n. So this is even, so 2 must divide b. So we have 2a to the n plus 3 times 2 to the n times, say, like b by 2 to the n equal 4c to the n. Now what you do is you divide by 2. So you get 2n minus 1, 2. You get 2 divides a now because n is at least 3. So this is even, this is even. So you once again write it as that. So you have 2 to the n, a by 2 to the n plus 3, 2 to the n minus 1, b by 2 to the n equal 2c to the n. Once again, you cancel out 1, 2. So this is n minus 1. This becomes n minus 2. And since n was at least 3, c is also even. So once again, you will do the same thing. And once you cancel stuff out, you will be left with this. 2a by 2n plus 3 b by 2n equal 4 c by 2n. And if you notice, this is the same equation, but earlier we had solutions a, b, c. Now we have solutions a by 2, b by 2, c by 2. We do the same thing again. We will get solutions a by 4, b by 4, c by 4. And this way, we keep getting smaller and smaller solutions to the equations. In particular, look at this quantity, sum a plus b plus c. Oh, no, let's do this. Sum a plus, wait, these are positive integers, right? Okay, we don't even need to take absolute value then. Yeah, the sum of solutions, like the sum a plus b plus c, this keeps halving at each step, right? But we know that this is always an integer, and there is no infinitely descending sequence of integers. So this must have been, in fact, 0, but that's not possible because the problem wants positive integer solutions. So this shows for n greater than equal to 3, there are no solutions. This trick in general is called Fermat's infinite descent. You show that for any solution of an equation, you can find the smaller solution. Like smaller in some sense, like here the sense is like the sum of numbers. Sometimes it might be the product, sometimes it might be the sum of squares or something else. Yeah, but I'll get to that. In general, so from any solution, you generate a smaller and then you generate a smaller. And well, this is not supposed to happen because integers, you cannot, positive integers, you can't keep it going down. So this proves that there are no solutions. For n equal 1, this doesn't work. For n equal 1, in fact, we do have a solution. The question asks which positive integers n, there are solutions. Right. So for n equal 1, and there is solution. N greater than equal to 3, there aren't. N equal to, we have not done anything yet. Now try the problem for n equal to. Yeah, made the same mistake. I get that. Mod 8. Okay, yes, we can do mod 8, but there's also the same solution, I think. Wait. Yeah, there is. Or- what? Yeah, makes sense. Anyway, so the argument we did above, it proves B is even, and then it proves A is even, but it doesn't prove that C is even. So what we will have is we will end up with 8 times A by 2 square plus 12 times B by 2 square equal 4 times C square. We'll cancel A by 2, I'll just abbreviate as A prime now. 2A prime square plus 3B prime square equals C square. And now we are stuck. We can't actually conclude B and C are even. But now you can once again do descent on this equation in a different way. Okay, so guys, there are a bunch of squares. What modulo do you want to take when there are squares?
8.
Okay, 8 works, but
3.
yeah, 8 will work. So one solution is you take mod 8 and you verify that there are no solutions to this equation mod 8. 4. But the thing is, we already like got as far as we can get with like just even or odd. Like 4 doesn't actually lead to anything. 8 does,
7
and you can do
also,
that.
7 and 9 stuff.
7 and 9 plus square. There's a much okay 9, yeah. But you can in fact just do 3. When you see squares, you should think mod 3. So reduce mod 3. This is 0. This is minus 1. So we have minus a square, well, a prime square, but whatever, equals c square. If you remember, squares modulo 3 are either 0 or 1. So 1, 8, a square can't be 1 because minus 1 is not a square. So a has to be 0. Similarly, c has to be 0. So a and c are both divisible by 3, right? So a square and c square are divisible by 9. So 3b square is divisible by 9. So b is divisible by 3. So now you descend with 3. So from a dash b dash c, you get a dash by 3, b dash by 3, c by 3. This is IOQM problem. Just slightly harder than IOQM. This is Putnam 2024 one, I think. Should have been IOQM. The chat. Don't look. Okay, Anirudh, I'll tell you something. There are few people in few characters in chat here. Riyansh, K. Gupta. Ignore these two. Just ignore everything they say. IOQM 2023 harder than Putnam for real, for real. just just ignore everything they say. Anyway, okay, does everyone understand this problem and in general understand what infinite descent is? Okay, I think if anyone has any doubts, feel free to speak up. Otherwise, let's move on to the next problem. Okay, okay. I is putting. Wait, who are you saying is joking? Me or the? Okay.
So you, I suppose.
No, no, this is actually a Putnam problem. I'm not lying. Okay. Don't. Yeah, also add to that list of people I said to ignore, add God of Death to that list. IMC live solve when? Soon, soon, soon. I don't know what IMC is, but soon. Okay, guys, let's try this problem. Once again, this is another problem of infinite descent. That's your hint. IMC equal IM college. Ooh, nice. Okay, so does anyone have any ideas? Once again, I'm ignoring the people I said to ignore. Keshav has done this problem before, right?
No, I solved it
Once,
here.
oh, you solved it right here.
Yeah.
Okay, wait, well, you can try like 2015 N4 if you're done with every problem in the class. Have you done the RMM problem? The
Which
last
one?
problem. Have you done this problem before?
Yes, I did do it.
Okay, try 2015 N4 if you have done all the problems with class before.
All right.
I'll ask you for the solution for this in some time. Try. This is RMO. Okay. One letter you have to change there.
He's asking if it is I.
It is not. It is not RMO. If you might be in trouble if you solve IMO. Wrong letter. Wrong letter. Anyway, other than Keshav, who else is new here? Anirudh and what was that? Shreyansh. Have you done P4 before?
I thought I did, but no. I saw the similar. I saw a similar
Ah,
problem.
okay.
Yeah.
Okay. Nishkarsh, have you seen this before?
No.
Oh, okay. Okay, good. So all of you guys, you can try this problem. I'll give you some time. By the way, for those wondering, although I think these have been spoiled enough times, this is 1950. The first problem we did, P0. This 1959 one. This is folklore. Two. This is Putnam 2000 P2. This is Putnam 2020. Wait, was this 4 or 5? Does anyone remember?
Is
It was
it
somewhere-
tab open in the top?
It's 4, I think.
You have the solutions tab open. Has
Shush.
the year written on it.
Okay, okay. Wait, why did it open in this one? I thought I had opened it. I was checking if there's any other solution. Because someone said this can be solved without infinite descent, but the official solutions didn't have anything else.
Yes. It,
I mean, it can. I believe it can be. I don't know what solution they're talking about. Anyway, P4. Okay, I have already spoiled the P5 source. P6. It can be any problem in the world. It's not like this is the world's most famous problem. And this one is APMO 2001. Which APMO is this? Doesn't even remember.
I think it is 2017 only, since 2017 is there.
That would make sense, you know. That would make some sense. APMO 2017 and P7 is
Oh, RMM.
This was
wrong letter.
my first RMM problem solved.
I think this might have also been my first RMM problem solved. Actually, there's this guy I knew who kept spamming me with RMM problems last year. This was the first one I did. Yeah, anyway, so you guys can try it for APM calls. I agree. Devayu, I think that might be the same friend. 2018 RMM. Devayu, I think it's the same friend. Oh, okay, it's a different fruit. My 7 key broke. Anyway, okay, people, the people who are trying it for the first time, any ideas for this problem before? Adding stuff up.
Can we like take two consecutive tuples of numbers in a circle and add up? That's what he said.
We get like
Hmm.
1 plus n6 is equals to 58, and in fact the sum of all the elements n1 and till n 2017 should be 29 times some 2017. I don't know if it's helpful or not, but yeah.
I
Yeah,
think
that's
we can
fine.
immediately eliminate that 29. Like
Wait,
29.
who's speaking? Who's speaking here? Sanskar, you have seen this problem before.
The sky is speaking.
You can stop. You, yeah, I know you know. You forgot it. So real, so real. Yeah, you can get a plus f equal 29 times 2, but mm, it's not. And yeah, I see what you're saying, but I don't. Wait, will you get everything as the multiple of 29? I don't know. Anyway, so as Sanskar said, you can eliminate the 29. Try to think how you can get rid of the 29. Like, I can replace 29 by any number here. In fact, I'll put 1434 here. Nothing changes about the problem. Can someone tell why? Subtract everything by 29 with divide 5 by subtract everything by 29 is correct. Why divide by 5? Oh, yeah. So the point is, if like a minus b plus c minus d plus c is 29, I don't understand why everyone's obsessed with the 1434. Hmm. Bro thinks he can avoid losing the game. Then we have this. Okay. Does everyone see this? Wait, who are you shushing?
I guess the last term is e.
Yeah. Oh, whoa, 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 whoa. This is yeah. Anyway. Anyway,
Just
so
to
as
just to ask something, can I just change the ink color to something that's darker? It's not very visible.
oh, okay, wait, how do you less dark or more dark?
Darker, more dark.
Okay, okay, that works. Anyway, okay, so if a minus b plus c minus d plus c is 29, then you notice a minus 29, b minus 29, like with these numbers, it's 0. So what you do is you take whatever numbers there are around the circle and you subtract 29 from each of them. And then you can rephrase the problem in terms of this sum just being 0, which is much easier. Okay, now what? Maybe can we get a non-white background? How do I? Oh wait, red works great on this background. Is this fine for everyone?
Like can't we get like an minus 1 plus an is equals to 0, because like there are 2017 terms, and uh, first 5 terms sum up to 0, so like multiple of 5 it goes till 2015, and an minus 1 plus an minus an is equals to 0.
Hmm? Wait, let me see what you're saying. A plus f. That's 0, 5, 5, 5, 5, 5, 5, 17. That work. I think that will. Wait. So yeah, I see what you're saying. So doing like okay. So now we have rephrased the problem in terms of zero. Oh, sorry, Lavish, have you not seen this problem before?
No.
Okay. Then it's fine with you trying.
But so after you rephrase the problem, it doesn't really matter how you arrange these numbers, right?
It does. It does, right? Why does it not? It's
Because
still the consecutive things that have to become zero.
Yeah, exactly.
yeah, that I got.
Hmm.
In the first statement, it's written we call a phi tuple of integers arrangeable if they can be labeled in some order, right?
Huh.
If they're summing up to zero, then the labeling does not matter, right?
They are not summing. Some are differences.
There are
So
some,
like
yeah, wait,
Some of these are minuses.
I got it, yeah.
we can get
Also,
like
yeah,
all
okay.
of them are zero.
I read this previous lemma also doesn't work because it might be that B, C, D, E, F and A, B, C, D, E. These are arrangeable in different ways.
Yeah,
So you can't even do like what you were trying, Lavish. Like you can't try to add these equations because they might have like a different arrangement that works.
Oh, I see. Okay.
Okay, but that's a good idea. Like this arrangement condition is very weird because, and the reason that this still matters is because some are plus and some are minuses, right? Is there a way you can make them all pluses?
Mod 2.
Perfect. Oh, wait, Keshav, you have done the problem. Oh, you did it today, so it's fine. Yes, plus and minus are the same thing mod 2. So you write this condition, and this condition is not dependent on them being in any order. And now you can do the previous kind of lemma that we were trying. So B plus C plus D plus E plus F is also congruent to 0, mod 2. You subtract these equations, and you get A is congruent to F mod 2. Right. In fact, what you actually get is like AI is congruent to AI plus 5 mod 2. Does everyone see this?
yes, also, can you increase the thickness of it, please?
Okay. Yeah. And similarly, this is congruent to, why is this green now? No, I don't care. AI plus mod 2.
Green is fine.
Yeah. Which is congruent to AI plus 15. And does everyone see that this runs, okay, everyone knows that this will run through 5 and 2017 are co-prime. So this will run
Yes.
through all the numbers. Right? So you start at say A1, or like, okay, start at A0, then it's 5, then it's 10, then it's 15. And since 5 and 2017 are co-prime, the A0 is just A2017. That's right. Since 5 and 2017 are co-prime, this will run through all the numbers. Like multiples of 5, like you multiply 5k can be any value you want mod 2017. This always has a solution. Okay. And so you get all the numbers are equal mod 2. Is that clear to everyone? Yeah, I think so.
Yes.
Okay. Now can anyone finish from here?
Now it's done, right? Because you're just adding or subtracting even numbers you're never going to get an odd. So,
No. We rephrase from 2019 to 0.
oh yeah, sorry. Yeah.
Why 2017 not 20? Problem has 2017. What?
Just keep on dividing 2 from the sum.
Precisely. So all numbers are equal mod 2. So they're all odd or they're all even. But they can't be all odd because they sum to 0. So they are all even. So now divide by 2. If you divide all numbers by 2, they still sum to 0. But by same argument, you can divide by 2 again, and again, and again. And by infinite descent, the only way this works is if all the numbers were 0, because you cannot divide any other number by 2 infinitely many times.
Wait, like, can you repeat? Why
Okay.
dividing?
All numbers are equal congruent mod 2. You understand that?
Yes.
Okay. And since any 5 numbers sum to 0, like mod 2, that means
Yes.
all 5 in fact have to be 0 mod 2.
Yes.
So in fact, every number is even,
Yeah.
right? So this condition, if you notice, if A, like not the 29 condition, after we have rephrased it in terms of 0, if A, B, C, D, E satisfy this condition, then so do A by 2, B by 2, C by 2, D by 2, E by 2.
Ah,
Right.
yes, yes, indeed.
So divide everything by 2, the condition still holds. But then by the same proof, the conditions you can divide by 2 again. And
Okay, yeah.
infinite descent, all must be 0.
Okay.
So this was APMO 2017 P1. Okay, Anirudh had seen this. Yeah, forgetting lemma is a very real thing. We all suffer from them. Okay, what's the time right now? APM also. Oh, we only have 10 minutes left. Okay, then I can't cover Vieta jumping in this class. Very unfortunate. we will we will cover Vieta jumping one day.
1988 P6 requires a full class. Like,
That's it.
like it was given like at least 1 hour in the exam. Like,
Yeah, that problem. Yeah, of course. Like back then, it's like very hard, but like with the benefit of hindsight, maybe. Okay, IUPM test. Okay, bye. Anish. I mean, I'm also leaving in 10 minutes. I also have to leave today.
put it
Okay,
on the OMC P set.
what?
Put 1988 P6 on the OMC P set.
No, I can't do like I have to give some at least one example of Vieta jumping in class before putting it on the P set.
There are some simpler examples, right? Like that
Mm,
triumph and A square plus B square plus C square equals 2ABC or
uh,
something.
yeah, okay, I can do that. Yeah, put something stronger. Okay. Okay. Anyway, let's quickly do this problem. So once again, I'm ignoring the people I said to ignore earlier. Is the last problem supposed to be last problem as in P7 or P6? Nishkarsh. The APO, as in the last one we did. Oh, this problem. This could be what? Inmo? Like early Inmo. Inmo P1 or P2. Not P1 might be too easy. Early Inmo, yeah, is it too hard for this is much harder than anything last year RMO. Although the previous RMOs I don't know about. Like if we compare with last year's cycle, okay, last year's cycle it could have been Inmo P1. That's the closest problem. It's harder than anything in RMO last year. Anyway, so once again, ignoring the usual suspects. One, um, Nishkarsh, Keshav have try P5. And even then, I would say this is like
Happens.
this could still be an
No,
Inmo
I've done
problem.
this problem earlier.
Oh, you already
So,
done this problem. Okay,
yeah.
that's okay. That is. Any ideas? This one's a much harder application of descent. I completely forgot this problem. Likely story. Okay, but fine. Okay, I'll open this up to Sanskar to try. I might end up regretting this.
Okay, so like
Hmm.
the sum of the roots of both equations are 0.
Okay. Okay, so I'll let alpha 1, alpha 2, alpha 3 be the roots of the first equation, and beta 1, beta 2. Vague memory of fake solving this. That's also fine. Okay, this is true.
Like we could say that the product is of alpha 1, alpha 2, alpha 3 is B.
With what?
B minus B.
Minus b, yeah.
And similarly write the pairwise product.
Beta equal minus a, alpha equal minus b, and bring over to a, and I did it using v2.
How are you going to use descent on this?
Yes.
Just watch me.
I,
Okay, not
I used
okay. It's
V2 on
not
this.
exactly the same. I mean, the idea is I'll prove that they are divisible by in 2 to the infinity.
Yes, that's what I meant. I used V2 in my solution.
Yeah, but like, it's close enough to the same. That's fine. It's fine. Is that pi? What? Oh yeah, this is pi. This means the product. Okay, yeah, these are the I have written down Vieta's relations.
Now add the second and third and first and fourth and equate them to the first equation.
Wait, give me a second. Give me a second, wait. Yeah. Add which equations?
Like minus
Things that
B, like the equations which have RHS minus B and B and the minus.
summation alpha I plus summation beta I plus 1.
I think you mean pi alpha. There are,
Summation but equal summation beta I, but this doesn't.
and that is also equal to summation pi beta I plus summation.
Equal. And also like anyone else with other ideas of what is the motivation for adding? He just wanted to create zeros. I mean, I think he's just trying random things. This is not a solution yet. It might be soon. Motivation for adding is just you see b and minus b, you want to cancel them. There is nothing special. Can you explain it? Explain what, Nikhil? Currently, we have not done anything in this problem. This is not a solution. No. We are trying it. I mean, I know the solution. This was Sanskar's attempt, but he stopped in the middle. This is not a solution yet. I was just writing down whatever he was saying. Anyway, other people,
Okay, we might
can
be
we
able to
use
bound like summation alpha I minus pi alpha.
wait, one short something? Can we use rational theorem? Maybe. Few, what? I don't get what you're saying. I love complex bash.
I think all alphas and all betas should be even.
All alphas and all beta should be
Even.
okay. Why? Also, wait, Anirudh, what were you saying?
I said all alphas and all betas should be even.
Oh, wait, never mind. Sorry. That's what you were. Brain freeze. Yeah, okay. Can you prove that?
Yeah, so there can be two cases of betas. So beta 1, without loss of generality, let's assume beta 1 and beta 2 are odd. and beta 3 is even. So
Okay. Why can't all, okay, all can't be all, like, yeah, because they
yeah.
add to zero. Some, yeah, fine.
So if beta 1 and beta 2 are odd and beta 3 is even, then beta
Hmm.
1 and beta 2 would be odd, and the rest of the, I mean, beta 2, beta 3, and beta 1, beta 3 would be even.
Yes.
So this implies that alpha 1, alpha 2, alpha 3 should be odd. And then that can't happen because alpha 1 plus alpha 2 plus alpha 3 is even, which is 0.
Yes.
0, which is
And they
even.
are all can't be odd. Okay, that works. Uh, the like sort of cleaner way to say that I would say is like, I mean, yeah, that is perfectly correct. The way I would write it is like summation alpha is zero, so at least one of alpha I is even. That implies B is even, and summation B, like, because B is the product. Summation beta is zero, so at least one of beta is even, so A is even. Since A and B are both even, um, since A and B are yeah, since A and B are both even, that implies that take any root of this equation, like any root. So we have alpha I cubed plus A alpha I plus B equals 0. So B is even, A is even. So these two things are even. So alpha I also has to be even. So that proves all alpha I are even. And similarly, all beta I are even. But yeah, your proof also works completely fine. Nice. So we have lemma 1, 2 divides alpha I, 2 divides beta I. And in fact, you can just use this to say 8 divides A implies 8 divides B. I mean, the other way around, I guess. But yeah, because it's a product. Anyway, okay. So here's a question. Can it be that all alpha i's are 2 times an odd numbers? Like none of them are divisible by 4. Is this possible?
No, it's not.
Who said that? Okay, so yeah, why?
Because the sum has to be zero, right?
Yes, the sum has to be 0. If these were all 2 times an odd number, then the sum would be 2 times the sum of 3 odd numbers, which is an odd number. But 0 is not 2 times an odd number. So at least one of alpha I is divisible by 4. At least, right? What can you say using this? Similarly, say alpha 1. Similarly, at least one of beta is
That
divisible by
means
4.
that all of them are divisible by 4, right? Because we looked at the earlier summation, which is that summation of alpha I, alpha I plus 1 is equal to minus B. And we showed that A divides B itself.
Summation alpha plus
A,
1 is.
sorry, it's A. And we showed that A divides A. And now,
Yeah.
if alpha 1 is divisible by 4, and let's say that
Mm.
the other two are not divisible by 4,
Then that's a contradiction.
yeah, that's a contradiction.
So you get at least 2 of them are divisible by 4.
Yeah, sorry, yeah, at least two.
Like if A comma B works, then A by 4 comma B by 8 also works. So we are done.
No.
Why?
Wait, what?
Yeah, if A comma B works, then A by 4 comma B by 2 actually works. B by 8.
No, but then the second equation becomes a different equation.
Can we write
That becomes
everything just with V2?
Okay.
Like, I think it would make the solution a lot easier.
write everything with what?
V2.
V2.
Yeah.
Huh?
Like, V2, like the two adding thing. So, like, I think
Oh,
like
V2. You're saying V2. Yeah, okay, we can, but technically, like, there has never been an OMC class of p-adics. But okay, fine, I'll just tell you that. When I say V2 alpha 1, I mean the highest power of 2 dividing alpha 1. So we have proven this is great, at least 2. Okay, yeah. So as someone pointed out, we have also proven that at least, okay, I don't like V2. We have also proven that at least two of them must be divisible by 4. Right. What about the
And
third? Can you also prove alpha 3? Is this possible? Like, must alpha 3 also be divisible by 4?
no,
Wait, isn't it the same thing?
What's the thing, right?
Like just sum is zero, so therefore.
Yeah, precisely. Wait, no, doesn't work.
It if
Oh,
if
it does. It does. It does. It does. Yeah.
yeah,
Alpha
some
3 is,
that works.
alpha 3 is minus alpha 1 minus alpha 2. So it's also divisible by 4.
Wait, can you explain how alpha 1 and alpha 2 both are divisible by 4?
Okay. So we first prove all are divisible by 2. Right. That's
Yes.
clear.
Yeah.
Now, or at least one must be divisible by 4. That is clear.
Yeah.
Okay. So suppose alpha 1 is divisible by 4. Right. Now, we have summation at like we have alpha 1 alpha 2 plus alpha 1 alpha 3 plus alpha 2 alpha 3 equal what, minus, no, this plus equal. So a is divisible by 8, this is divisible by 4, this is by 2, this is by 4, this is by 2. So these are divisible by 8, this is by 8. So this thing has to be divisible by 8. And
Yeah.
both are even. At least one must be divisible by 4. Because if both are just like 2 times odd number, then we can't get a multiple of 8.
Yeah, I got it. Thank you.
So alpha 2 is also divisible by 4. And since alpha 3 is minus alpha 1 alpha 2, that is also divisible by 4.
Wait, so now
Right.
can you just divide everything by 4 and then get me no solution?
That doesn't work. A and B change weirdly, unfortunately.
Maybe
Wait, yeah. The point is like, if you divide by 4, then this equation, like, this equation says A should be divided by 64, but this equation says A should be divided by 16. So you don't really know what A to take in the new equation.
no, I mean dividing A and B by 4 and then still showing that
Oh, then why does it still have roots? That's not
it
proven.
will, right?
Why?
No, wait.
Like, you can't exactly dissent in this problem. Like, you can prove they are divisible by high powers of 2, but it's not technically dissent.
Yeah.
Anyway, let's see what we have. So we have proven 4 divides alpha A, 4 divides beta A, and in fact this implies 64 divides A implies 64 divides B. Right. Okay, now do the same thing, get to 8.
Okay, so we are showing that higher and higher powers of 2 divide
Yeah.
alpha and beta,
Yes.
and that's a hundred.
In fact, we are going to induct infinite ascent. Yeah, okay, this is infinite ascent. That's what we are calling it. Anyway, in fact, yeah, I'll just write the full claim. We are inducting on this claim. Action on 2 to the k divides alpha A, comma beta A. So we have proven that base case for k equal 1. We have in fact even shown the induction step for k equal 1 to k equal 2. Write down the general induction step. This is slightly more tricky, but okay. Try to go from 2 to 3. How will you do that? Anyone?
Yes, so we can now finish by induction. Like we can
No,
write.
how do you induct? You have to.
Yes. Yes. Okay, so now you write alpha 1 alpha 2 plus alpha 2 alpha 3 plus alpha 3 alpha 4 is equal to
Alpha
that-
4.
alpha 3 alpha 1 basically. Now we obviously know that like 2 to the 3k divides a. So
Okay. Divisible by 2 to the 3k.
now
That
like alpha 1 plus alpha 2 plus alpha 3 is equal to 0.
alpha 1 plus alpha 2 plus alpha 3 equal to 0. That is also something I know.
Now you can say that at least one of them has to be divisible by 2 to the k plus 1.
Yes. As we did earlier, everything can't be 2 times odd number, or in general, everything can't be 2 to the k times odd number. Because odd plus it's then it will become 2 to the k times odd, which is not 0. So say alpha 1 is divisible by 2 to the k plus 1. Now what?
Now we can say that if alpha 2 and alpha 3 are also divisible, if any one of alpha 2 and alpha 3 are divisible by 2 to the k plus 1, we are done. So just assume
Yes,
that.
because then the third is divisible by 2 to the k plus 1. So
So just
assume neither are.
assume their maximum power is 2 to the k.
Yes, so they are both 2 to the k times odd number.
But then you can see that like alpha 1, alpha 2, alpha 1, alpha 3 is divisible to the k plus 2 to the 2k plus 1. While alpha
These are
2
divisible by 2 to the 2k plus 1,
is 4.
2 to the 2k
But the
plus
middle
1.
term is but the middle term is replaced with the 2k.
Yes, this is divisible by 2 to the 2k.
Again,
So this whole thing cannot be divisible by 2 to the k plus 1. But we know it is. Hence we are done. It's 2 to the k times odd number, it's a fact. Like alpha 1, alpha 2 is divisible by 2 to the 2k plus 1. Alpha 3, alpha 1 is. So alpha 2, alpha 3 has to be. But we just said it's 2 to the 2k times odd number. Contradiction. Yeah, that works. That works, Samska. Okay. Does everyone understand that proof? Anirudh, Vansh, Nishkarsh,
Yes,
is
I
this
do.
medium or hard or easy in Mo? Yeah, okay. I think, okay, everyone understands this. How hard is it in INMO terms? I would have to think. I have only given like 2 INMOs in my life. This is, I think, honestly, this might be harder than anything that appeared on 2024, but compared to 2024 was also like an exceptional year. Uh, it's not an easy problem. It's medium or hard, I would say. What do others think? Like in INMO terms. Like this is in like on other years it would not have been
Be
V2.
in no problem too.
What?
It should be in no problem too.
It should be in no problem. Well, so too. I mean, most rating is probably still. Most rating might be 5, 5 or 10.
Then it will
5 also.
most
Actually, might be 10.
most
Not
8 or something.
8. Yeah, makes sense. Somewhere between 5 and 10. Low 5. No. Right. Not low 5. Have you seen the kind of things that get 5 these days?
Only for OS people.
No, like, have you seen the things that get 5 these days? Like, I would say this is harder than like IMO P4 is 15 most for some reason this year, and I would say this is harder than IMO P4, but
MOP4 was simple, but it was very hard to write up.
fair enough. That's why it's what, mm, nightmare to write up. I have been there. I struggled through it. Yep. Anyway, okay. So I think I don't have enough time. We can Vieta jumping some other day. RMM RMM we'll see. RMM this problem is very nice. I mean, this wasn't meant to be in this class. This was just because too many people have seen stuff before. Anyway, I think that's the end of this class. This class was slightly skill issue compared to my normal classes because I think a lot of people had seen the problems I chose this time. But I hope all of you enjoyed, and I hope all of you like. Okay, the theory part was very short this time. I hope all of you like understand why understand these kind of ideas, just descents and like if a number is divisible by high powers, then it's 0 and whatever. Yeah. Okay. Does anyone have any questions? Otherwise, we can end. P4 length was more than P6 length. Okay. With K Gupta, see the write-up by me on AOP. Oh, for P4. Yes, fine. You can self-promote. Can I still get into Sophie? I don't. You'll have to ask someone. I don't know. You can always apply next year. I I'm not involved with like the application and stuff.
Dictator or Sophie student?
What?
Are you Sophie dictator or Sophie student?
Me?
Yeah.
He's
I
neither.
mean, I'm BDM. Yeah, I have not been given full dictator power yet, unless it's quote log.
Oh, yeah, just in the role.
Yes. I'm just a instructor. Well, I would take a class, Sophie class one of these days.
Yeah.
It's just
You've taken what, like 4 OMC classes, right?
yeah. This is my fourth OMC class.
Yeah.
So they didn't need OMC. They need me. Sophie, they usually find other people to instruct, and they don't have to resort to me. Very sad. Anyway, okay. Actually, speaking of which, both OMC students and Sophie students, is there a lecture you would like me to take? Combo. Oh, damn. Okay, some normal lectures, guys. What should my like next OMC lecture be? What have you guys solving the whole Putnam? Nah, but that's
Stuff like Jensen's and all. Like
oh,
derive full Jensen's and with convex and concave and all. Or you could also do like in geometry something like projective maps and all.
yeah. I would love to do some projectives. Though I think if no, I would never probably be taking any projective class from me. But I would be happy to do some projectors. Please, I'm dying. Wait, what's I love complex by saying? Computational combo for IOQM. Oh, no, 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 no. Please, don't make me do this. Expected value and Markov chains. Okay, interesting, interesting. Okay, for Sophie, that's
Wasn't
fine.
that done in the crypto classes and so? So,
Crypto.
this is
Oh,
directly said to Sanskar.
ah, trigger to the Anyway, for OMC, what topics are left? I think with this class, all of intro NT is finished, right? There is no introductory topic in NT left. Now it's just the more advanced stuff. Primitive roots is not intro NT. Weekly classes on complex bash. Now we are talking. What?
Primitive root
Bash?
intro and
No, it's medium. But come on, bro. I learned primitive roots last year, like before Inmo. Like, come on, bro. Intro NT I'm defining as anything like you need to know for RMO. So like that was like modular arithmetic, division algorithm, Bezout's lemma, Fermat's and Euler's. Do you support Bash? I love Bash. I bashed in IMO. I bashed in
everyone bashed
TST.
in IMO.
What?
Everyone bashed P4.
No, I'm talking about P2. I
How
bashed
bashed
P2
P2?
complex. My respecting. Thank you, thank you.
But there are 2 circles. How did you survive that?
The circles are a lie.
Yes, that is true. Like I got P is the AX center in that triangle.
It's a
Like
wrong triangle. I matched with triangle PMN. You do triangle PMN, then eh, you prove that A lies on the diameter line. Like O is the circumcenter of
oh
PMN, then A
yeah,
lies on this line
I see.
by angle J's. And then you can like define every single point in terms of reflections.
Okay, yeah,
Like
that's
and then
actually
you finish. Everyone
my
is on
my
stage.
my philosophy in geo problems is like use synthetic as much as possible and
Hmm.
use complex if and only if needed.
Yeah, so it's a series. That's like close to my philosophy, but my as much as possible was proving this is diameter line by angle J's. And then I'm like, okay, now compute. It's over. Advanced NT.
How much did
Yeah,
you sorry? How much did you
uh,
get for P2?
7. P1, P1, P2, P4, P5, 7, 7, 7, 7. It's like,
Nice.
give me some. They gave me some. They had to argument. Like the graders did not like me. I would tell you that
For
for
what?
P2. For P2. Like everyone else had synthetic in the team. Like very nice solutions, and then I was there. Like,
Right.
next lecture, advanced in orders and stuff. Yeah, orders we have to should do it. Like okay, wait. MP we are done with like all the like. Did we cover for maths and Eulers? Can someone who has attended all lectures tell me? Has for maths and Euler's theorem been done? For maths, Euler, Wilson. Did you fight kangaroos? No. I petted kangaroos. Yeah. Oh wait, why are we still recording? We should have stopped recording. I'm sure.